scientists made an impossible choice. They rappelled into the heart of a dying glacier, into a cave filled with poisonous gas to take the pulse of a mountain that Canada had forgotten was alive. And if their readings are right, a catastrophe is not a matter of if, it's a matter of when. Deep in the coast mountains of British Columbia, a massive ice-clad volcano sits in silence. It is the northernmost anchor of the same volcanic chain that produced Mount St. Helens. It is the site of Canada's last great explosive eruption. And until very recently, almost no one was listening to it. The mountain had been left for dead, dormant, harmless. It was not harmless. It never was. So a small team of explorers and volcanologists did something no one had ever attempted. They went inside the volcano itself, through a wound torn open by its own internal heat, to find out just how close it was to waking up. They called it a necessary risk. What they found should have set off alarms across the country. But here's what most people don't know. The mountain is still breathing. The glaciers holding it together are vanishing. And an entire region is living downstream from a geological time bomb that has been ticking for over 2,000 years. The real question is, did the expedition just give us a fighting chance, or did they only confirm that it's already too late? The Mount Meager volcanic complex was never meant to be a secret. It is a sprawling massif of overlapping lava domes and eroded peaks, visible for miles. A giant of the Garibaldi volcanic belt. Yet for generations, it has existed just beyond the edge of public consciousness, overshadowed by its more famous American cousins like Mount Rainier and Mount St. Helens. Those volcanoes have armies of sensors listening to their every rumble. Mount Meager had almost nothing. For decades, the official stance was one of passive observation, a geological curiosity, not an active threat. This was a dangerous assumption. Nearly 2,400 years ago, a vent on the massif named Plinth Peak erupted with cataclysmic force. It was a Plinian event, a volcanic explosivity index of 4, the same class of eruption that buried Pompeii. A colossal column of ash rocketed 20 kilometers into the stratosphere, visible for hundreds of miles. It blotted out the sun. Pyroclastic flows, incandescent avalanches of gas and rock moving at hurricane speeds, scoured the surrounding valleys, vaporizing everything in their path. The ash fell as far away as modern-day Alberta, the Lillooet River. The region's lifeblood was choked with volcanic debris, forming a massive dam. The valley flooded. Fish runs collapsed. The local Lillooet Nation, who call the mountain Quo Welwelusten, or roasting place, were forced to abandon their homes and flee. Their oral histories preserve this moment with chilling accuracy. One story of the Copper Canoe tells of a time the mountain exploded, the river ran dry, and then returned as a catastrophic flood that reshaped the world. Modern geologists, tracing the ash layers and lahar deposits, would later confirm every detail of this ancient account. The people who lived at the foot of Quelcolustun had witnessed the last time it had truly woken up. And they never forgot. But modern Canada did. It built towns, highways, and infrastructure in the shadow of a volcano that had already proven its capacity for violence. The memory of the fire and ash faded into geology textbooks. The threat became theoretical. The silence of the mountain was mistaken for peace. The entire apparatus of modern life in the region rests on that mistake. The towns of Pemberton and Mount Currie, home to thousands of people, including over 2,200 members of the Lillooet Nation, are situated just 60 kilometers downstream, directly in the flood path mapped out by that ancient eruption. They rely on a river system that begins at the base of a volcano classified by Canada's own government as a very high threat. That is the same threat level assigned to Washington's Mount Baker, a volcano with a vast network of real-time sensors. Until recently, Meager's monitoring consisted of infrequent scientific flyovers and periodic GPS surveys. No continuous seismic network. No gas monitoring. No cameras watching for collapse. It was equivalent to having a hospital patient in critical condition, with no one checking their vital signs. Dr. Glyn Williams-Jones, a volcanologist at Simon Fraser University, put it in the starkest possible terms. If we're not looking, we can't take the pulse. We can't say, is the patient awake or not? For decades, Canada chose not to look. The problem with a volcano like Mount Meager is that an eruption is not the only way it can kill you. In fact, it might not even be the most likely. The greater, more immediate threat is the mountain itself. It's falling apart. Dr. Williams-Jones describes the massif with a single, unnerving word: rotten. Mount Meager is rotting from the inside out. For millennia, superheated, Acidic volcanic gases and fluids have been percolating through the mountain's core. This process, called hydrothermal alteration, is like a slow-acting cancer for a volcano. It cooks the hard, stable volcanic rock, the andesites and dacites, and chemically transforms them into soft, weak, unstable clays. The structural integrity of the mountain is literally dissolving. And for centuries, only one thing has been holding these vast, rotten slopes in place: ice. The thick, heavy glaciers clinging to its peaks act as a kind of geological glue, a cryoscaffolding buttressing the crumbling rock. Now, that glue is melting. As global temperatures rise, the glaciers on Mount Meager are in a state of rapid retreat. As the ice thins and pulls back, it exposes the weakened, oversteepened rock to the elements. The support is gone. The failure is becoming inevitable. This isn't a theoretical model. It's a documented reality. On August 6, 2010, at 3:27 in the morning, it happened. The entire southern peak of Mount Meager collapsed. With no warning, nearly 50 million cubic meters of rock and debris, enough to bury a city block under a 200-story skyscraper of rubble, let go at once. It was one of the largest landslides in Canadian history. The avalanche of rock screamed down Capricorn Creek for over 7 kilometers, moving so fast and with such force that its momentum carried it hundreds of feet up the opposite side of the valley. It was so violent it registered as a magnitude 2.6 earthquake, with seismic waves detected as far away as Alaska and Washington state. The debris dammed Meager Creek, creating a huge, unstable lake that threatened to burst and send a catastrophic flash flood down the Lillooet River toward Pemberton. It cost 10 million Canadian dollars in emergency response and destroyed critical infrastructure. It was a warning shot, fired in the dead of night, a clear demonstration of what a rotten mountain was capable of even without an eruption. And it still wasn't enough to change the fundamental equation of neglect. The landslide was studied, the reports were filed, but the core vulnerability remained. The mountain was still unmonitored, its internal state a complete mystery. No one knew if the landslide was a random event or a symptom of a much deeper problem. Then, 6 years later, a helicopter pilot stumbled upon the answer. On July 21, 2016, a commercial pilot was flying a team of biologists over the remote, icy flanks of the massif. It was a routine flight over familiar terrain. But as they passed high above the Job Glacier, they saw something that did not belong. 3 dark, gaping holes in the pristine white surface of the ice, each one venting a plume of steam into the cold mountain air. They were fumaroles, volcanic gas vents. But vents of this size and power had never been seen here before. They had melted their way entirely through the glacier from the bedrock below, creating vast subglacial caverns. One was estimated to be 30 meters wide, 30 meters long, and 30 meters deep. An entire cathedral of space melted out of a glacier by the volcano's hidden heat. The discovery sent a shockwave through Canada's small community of volcanologists. This was not the gentle, passive heat of a dying system. This was aggressive, active. The volcano wasn't just warm. It was breathing forcefully enough to punch holes through its own icy shell. The retreating glaciers hadn't just weakened the mountains. They had peeled back a blanket, revealing a far more energetic and dangerous system than anyone had been prepared for. The patient wasn't just awake. It was showing a fever. And the only way to find out how high that fever was running was to go to the source. A team would have to go down into those holes. The mission was unlike anything ever mounted on a Canadian volcano. It was a descent into an underworld of fire and ice, funded by the Trebek Initiative, a joint grant program from the Royal Canadian Geographical Society and National Geographic. The expedition was led by Christian Stenner, a veteran cave explorer and fellow of the RCGS. He partnered with Simon Fraser University's Dr. Williams Jones, whose research was now pointing to Meager as a site of imminent hazard. They assembled a small elite team, including fellow caver Kathleen Graham, capable of operating in one of the most hostile environments imaginable. The goal was to do what had never been done: enter the subglacial fumarole caves, measure the volcanic gases directly, and get a true reading of the magmatic system's activity. It was a plan that was audacious in its simplicity and staggering in its risk. Getting to the caves was the first ordeal. Traveling across the fractured, crevasse-ridden surface of the Job Glacier is treacherous on its own. Now they were aiming for a specific weakness, a place where the glacier was being actively undermined from below. The air near the vents was already thick with the rotten egg smell of hydrogen sulfide $H_2, a gas that can be lethal in high concentrations. A fall into the wrong crevasse wouldn't just mean injury. It could mean instant asphyxiation. Standing at the edge of the main cave, the team confronted a scene from another world. A chasm of scalloped ice walls descended into darkness. From its depths, a visible plume of steam and gas pulsed upwards, carrying the heat of the earth. The sound was a constant low roar. The voice of the volcano itself. Christian Stenner and Kathleen Graham were the first to go in. Rigged to a web of ropes anchored into the precarious ice, they began their rappel. They were equipped with multi-gas detectors, scientific sensors, and most critically, respirators. The atmosphere they were descending into was unbreathable. Inside, the world transformed. The ice walls glowed a translucent blue, lit by their headlamps. The floor was a jumble of collapsed ice blocks and rocky debris. And everywhere, gas vents hissed from cracks in the bedrock. The heat was intense, a stark contrast to the glacial ice enclosing them. This was the place where the deep earth met the frozen surface. The team took measurements. Temperatures were high. Concentrations of carbon dioxide, $CO_2, and hydrogen sulfide were at dangerous levels. But then their sensors picked up something else, a gas they were hoping not to find. Sulfur dioxide, $SO_2. As Christian Stenner later recounted, on our way back out, we hit all the volcanic gases. It was like the volcano had burped. We were hoping to not find sulfur dioxide because that's one of those gases that is more indicative of an active magma chamber. This was the smoking gun. Hydrogen sulfide and carbon dioxide can be produced by a variety of geothermal processes. But sulfur dioxide is different. It is highly reactive and breaks down quickly, meaning that if you detect it at the surface, it must be coming from a fresh, shallow source. That source is almost always an active, degassing body of magma not far below. It was the clearest evidence yet that Mount Meager wasn't just a hot rock. It was a living volcano with a churning magmatic system, close enough to the surface to be sending its most potent chemical messengers directly into the atmosphere. The expedition had gone looking for a pulse, and they had found a heartbeat. The discovery inside the ice caves fundamentally changed the risk assessment for Mount Meager. The confirmation of an active magmatic system meant that a future eruption was no longer a distant, abstract possibility. It was a tangible threat, but the implications were even more immediate. The heat source that vented those gases was sitting directly beneath 75 million cubic meters of ice that make up the Job Glacier. A sudden eruption, even a small one, under that ice would trigger a melt event of almost unimaginable scale. The resulting flood of water would mix with the vast quantities of rotten, clay-rich rock on the mountain's flanks, instantly generating a lahar, a thick, fast-moving slurry of mud and debris with the consistency of wet concrete. That lahar would pour down the established channels of Capricorn Creek and Meager Creek, picking up speed and volume, and surge into the Lillooet River Valley. It would travel at highway speeds, a river of liquid earth that could overwhelm anything in its path. For the communities of Pemberton and Mount Curry, the warning time could be catastrophically short. The 2010 landslide proved how quickly the mountain could fail. An eruption-triggered lahar would be an order of magnitude more destructive. It's a scenario that has a chillingly modern precedent. In 1985, the Nevado del Ruiz volcano in Colombia erupted. It was a relatively small eruption, but it melted the summit glaciers, sending a series of lahars down the mountainside. One of them completely buried the town of Armero, killing more than 23,000 people. The town had received warnings for hours, but the threat was not understood. At Mount Meager, the warnings might only last minutes. This new grim reality was made even more complex by another, stranger discovery. The environment inside the Meager ice caves, the unique mix of ice, rock, intense heat, and sulfurous gases, is so extreme, so alien, that it's one of the best analogs on Earth for the conditions believed to exist on the icy moons of the outer solar system. NASA's Jet Propulsion Laboratory took notice. They partnered with the science team, using the caves as a testing ground for astrobiology equipment. They sent prototypes of rovers and sensors, designed to one day search for life on moons like Saturn's Enceladus, into the toxic belly of Mount Meager. The caves were a perfect stand-in, a dark, high-pressure, sulfur-rich environment where life, if it existed, would have to be incredibly resilient. In 2024, research was published detailing how instruments were tested there to hunt for signs of life in places far beyond our world. That a feature on a Canadian mountain is being used to simulate moons 1 billion kilometers away is a testament to just how bizarre and dangerous this place truly is. We are using a terrestrial volcano to prepare for space exploration, while the terrestrial threat it poses has been dangerously underestimated for decades. For years, the evidence mounted. A catastrophic landslide, newly discovered powerful fumaroles, direct gas measurements confirming a shallow magma source, the vocal warnings of scientists like Dr. Williams Jones and Dr. Melanie Kelman of the Geological Survey of Canada. And yet, the mountain remained a black box. The data from the cave expeditions was a snapshot, a single moment in time. But volcanoes are dynamic, they change, and without continuous monitoring, there was no way to know how. The local authorities knew the risk better than anyone. Kevin Clark, the manager of the Pemberton Diking District, spent years advocating, lobbying, and fighting for funding to finally put a permanent set of eyes and ears on the volcano that loomed over his community. Finally, the needle moved. It was announced that in the spring of 2026, Mount Meager would receive Canada's very first gold standard continuous volcano monitoring station. It's a massive step forward. The station will include a suite of modern sensors, a broadband seismometer to listen for the tiny earthquakes caused by magma moving through rock, high-precision GPS to detect the subtle swelling of the ground as the magma chamber inflates, infrasound sensors to listen for the low-frequency sound of explosions, and cameras to provide visual confirmation of any activity. For the first time, scientists will be able to track the volcano's behavior in real time. They will be able to take its pulse, day after day, week after week. They will finally have a chance to see a warning before the next disaster, not just analyze it afterward. But the relief is tempered by a sobering reality. This is one station on one flank of a massive volcanic complex. By comparison, Mount St. Helens is monitored by a dense network of more than 24 seismic stations and over 15 GPS instruments. To truly understand Meager, a full network is needed. The 2026 station is a critical start, a desperate catching up after decades of neglect. It is the beginning of a conversation with the mountain, not the end of the risk it poses. And recent science shows that the clock is ticking faster than anyone thought. A 2024 remote sensing study revealed that the debris from the 2010 landslide is not stable. It's actively eroding into the Lillooet River system at an alarming rate, continuously increasing the background flood risk for Pemberton. The mountain's past failure is actively shaping its future threat, a lingering poison in the watershed with a calculated half-life of 47 years. The landslide of 2010 isn't over. It will haunt the valley for generations. The installation of a monitoring station is not a solution. It is an admission of the problem. A problem that has been building for 2,400 years and has been accelerating for 20. The hard questions remain unanswered. What happens when the monitoring station hears the first definitive signs of an impending eruption? How do you evacuate thousands of people with potentially only hours or minutes of notice? How does a region built on the assumption of geological stability reckon with the fact that it is not stable at all? The science confirmed what the Lillooet Nation's oral history always knew. Qual Qualustan is not a dead mountain. It is a place of immense power that is only sleeping. The expeditions into its icy heart prove that its sleep is becoming restless. Mount Meager is more than a Canadian problem. It is a planetary symptom. A story of how quickly a changing climate can awaken ancient geological threats. The melting ice is the trigger, the rotten rock is the ammunition, the magma below is the fuse. We are finally starting to listen. The question is what the mountain will have to say. The 2026 station will turn the silence into data, providing the first continuous stream of information from the volcano's core. It might provide peace of mind, or it might provide the first terrifying notes of a symphony of destruction that has been rehearsing in darkness for centuries. The effort to understand Meager is not a story of scientific curiosity. It is a race for survival. The scientists have been inside the beast. They have measured its breath. But somewhere deep beneath the ice, a heart of molten rock is still beating, and nobody knows when it might decide to beat faster.